We're going to begin our discussion of probability today. And in doing so, we're going to talk about basic concepts of probability. So when we're talking about probability, we want to be able to interpret probability values. Probability is represented by a number between 0 and 1. The values closer to 0 are less likely to occur, and the values closer to 1 are more likely to occur. So we want to walk away from this lesson being able to look at a probability value like 0.001 and interpret it as corresponding to an event that rarely occurs. Also, we want to know what odds are and how they relate to probabilities because they're really commonly used in things like lotteries and gambling. So we have a little bit of vocabulary to knock out to start us off. So the first idea is that of an event. An event is a collection of results or outcomes of a procedure. So the procedure could be something like flipping a coin, where we might have heads or tails as the possible results. So the event is those results. So we have the event of flipping a coin and getting heads. All right, heads is the event. That is actually also considered a simple event. So a simple event is an outcome or an event that cannot be broken down further into simpler components. Right? So we're going to look at an example in just a little bit to get that difference between events and simple events ironed out a little bit more. But just remember, simple events can't be broken down further. Events could potentially. All right. Sample space is the list of all of the possible outcomes. So we take a procedure and we list all of the simple events. That's the sample space for that procedure. So let's take a look at an example. So we're going to consider having one baby be born, and we're going to use B for boy and G for girl. So if we have one girl is born, that's a simple event. It's a result and it can't be broken down any further. Similarly, one boy being born is also a simple event. If instead we look at 3 births, then the result of 2 girls followed by a boy, so I have 3 children born, first 2 are girls, and the last one is a boy, then we end up with this GGB, and that is also a simple event. Right. So something that you may encounter, like if you're rolling a die, a single 6-sided die, then you can get an outcome of 1, 2, 3, 4, 5, or 6. So the outcome of 5 is a simple event, but if you instead are talking about the outcome of an even number, that is not a simple event because an even number can be broken down into the simple events of 2, 4, and 6 as outcomes. Right? So translating that example with the die into what's going on with these 3 births, when we said that we had 2 girls followed by a boy, we had that simple event of girl, girl, boy. However, if we take away that followed by and replace it with an and, so we're looking at the event of 2 girls and a boy being born, now it doesn't matter what order they come in. And so we have the possibility of girl, girl, boy, boy, girl, or boy, girl, girl. So the event of 2 girls and a boy is not a simple event because it can be broken down into the simple events of 2 girls followed by a boy, a girl followed by a boy followed by a girl, or a boy followed by 2 girls. So this table summarizes all of that for us. With a single birth, we have an example of an event as 1 girl is born, and that's a simple event. And our sample space is boy and girl. And with 3 births, we have 2 boys and a girl as an event, And that's not a simple event, but then we have our list of 3 possible simple events that contribute to that single event. And we have our sample space, which consists of 8 different simple events. We can have all 3 boys. There are 3 ways that we can have 2 boys and a girl, 3 ways that we can have 2 girls and a boy, and 3 girls as possibilities. All right. So we have 3 common approaches that we can take to finding the probability of an event. The notation that we're going to use as we go through this, when you see the letter P, you should be thinking probability, all right? And capital letters A, B, and C are common ones, but other ones can be used, are going to denote specific events. So when we see the capital P and capital A in parentheses, we read this as the probability of event A occurring. All right? Sometimes we shorten it down to the probability of A. So again, we have this scale from 0 to 1 of possible probability values. And 1 is certainty, close to 1 is very likely, 0 is impossible, close to 0 is unlikely, and that 0.5 value is kind of a 50-50 split. Right. So let's talk about how we're going to find these probabilities, these values between 0 and 1 of an event A. So the first way that we can find this is finding the relative frequency approximation of probability. Right? To do this, we're going to conduct a procedure and we're going to count the number of times that event A occurs. And then the probability of A is just going to be calculated by taking the number of times that A occurred divided by the number of times the procedure was repeated. So what this might look like is flip a coin 10 times. What's the probability of getting heads? Well, if I flip a coin 10 times and 6 times I get heads, then I'll take the probability of getting heads as 6 divided by 10. So that first approach is sometimes called an experimental approach because we actually go through and conduct the procedure, we do it. The second one is sometimes called the theoretical probability because we don't actually have to do the procedure. We just know things about it in theory. So the classical approach to probability requires equally likely outcomes for all of our possible events. So if we have a procedure that has n different simple events that are equally likely, so our sample space has n elements in it, and all of them are equally likely to happen, and event A can occur in s different ways, right? Then the probability is going to be the number of ways that A can occur divided by the number of simple events that we have, or s divided by n. So it's really important that all of the outcomes are equally likely here, and you have to confirm that to be able to use this approach. Our third and final common approach to finding probability of event is considered subjective probability. So this is the probability of event A being estimated by using knowledge of the relative circumstances. All right, so we don't necessarily have this theoretical knowledge, or maybe our events are not equally likely to occur, and we have to use some kind of knowledge that we have about this. And because we're using our knowledge about the circumstances, it's considered subjective because my knowledge about the relevant circumstances might be different than yours, and consequently we would come up with different estimated probabilities. So sometimes none of those approaches are feasible. This can be due to time, cost, any number of things that we can't use any of the procedures that we just listed. Instead, what we might do is a simulation. So when we talk about having the birth of children, it might be time consuming to wait at a hospital for children to be born. But we know that the probability of having a girl and a boy is about 50%, which is about the same as flipping a coin. And so we might be able to simulate the outcomes of some number of children being born by flipping that many coins. It's an example of a simulation. All right, rounding probabilities. So when we're expressing things as probabilities, we want to give exact fractions or decimals that are rounded off. Our final decimal results, we want to give 3 significant digits. All right, so that might look like different things. This is significant digits, just like you've seen in any science class. All right, you'll count significant digits the same way. 3 significant digits is what we want. So whenever a probability is in fraction form and you look at the fraction and you go, I don't really know what that looks like how big that is, how close to 0 or 1 or like 50%, half, then you should probably put it in decimal form. All right. So we want it to be understood. So if you look at it and you don't understand it, whoever you're trying to communicate it to is also not going to understand it. So use fractions when they're easily understood. Use decimals every other time. And 3 significant digits is the magic number. So there's this really awesome law called the law of large numbers. What it tells us is that a procedure is repeated again and again. The relative frequency probability of an event tends to approach the actual probability. Right? So this is saying you flip a coin 10 times, you might not be too close to this idea of a 0.5 probability of getting heads. But if I flip a coin 1,000,000 times, I better be pretty close to a probability of 0.5 for getting heads. All right. Notice this applies to a large number of trials, not to like the next 5. You can't say I've been doing this all day, and so the next 5 are going to be pretty close to the actual probability. It's everything that you've been doing all day collectively is going to be close to the actual probability. Right. Also, remember that if we know nothing about the likelihood of different possible outcomes, we should not assume that they are equally likely. The actual probability depends on factors, and those factors can be just about anything depending on the procedure that we're doing. So let's take a look at an example. We're going to calculate the probability using the relative frequency probability to look at the probability of dying when making a skydiving jump. So to do this, we need to know how many skydiving jumps there was in a period of time and how many of them resulted in death. So in a recent year, there's 3 million skydiving jumps and 21 of them result in death. So we take the 21 deaths and we divide by the 3 million total jumps that happened, and we get a probability of dying when skydiving of 0.000007. So we look at that and we go, it's not very likely. And when we're talking about this, it's really important. We can't use the classical approach here because the 2 outcomes, dying and surviving, they're not equally likely. Very few people would skydive if dying and surviving were equally likely outcomes. Right? Subjective probability can be estimated if we didn't have that historical data. So you could say, how many people do I know that have skydived? And have any of them died? So you might come at it, I personally would come at it and say the probability of dying when you skydive is 0. It's impossible. So I would probably say, it probably happens every once in a while. So my subjective probability would be it's close to 0. It's rare. And yours might be similar. Or you might be unlucky enough to know somebody who has died when they were skydiving, and you might think that it's very dangerous and the probability of dying is very high. Again, that's why it's subjective probability. So another example, texting and driving. So in a study of U.S. high school drivers, it's found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving during the same time period. Right? So this actually came from a real study. Right? Based on these results, if a high school driver is randomly selected, find the probability that he or she texted while driving during the previous 30 days. So when we get something like this, we can't necessarily jump straight to probability. We might need more. So if I wanted to find the probability, I need to be able to divide by the total number of people that are asked. So instead of trying to determine an answer straight away, we need to come up with that total number of drivers that were in the sample that was taken. So to find that, we're going to add together the number that texted and the number who did not text. We add them together, we get 8,505 high school students were the number of drivers in our sample. So then we can find the probability of texting while driving by finding our number of texting while driving responses, so 3,785, and dividing it by the number of drivers in the sample, which is 8,505. We do that division, we take our decimal, we round it to 3 significant digits, and we have a probability of 0.445. So then we can interpret this and say there's a 0.445 probability that if a high school driver is randomly selected, they texted while driving during the previous 30 days. That's our interpretation of our answer. So now let's talk complementary events. So another vocabulary word to throw at you. This is complement, not compliment. All right, there's a difference. So compliments are nice things you say to people. A complementary event, or the complement of some event A, is the event that it doesn't happen. Okay, so we use the notation of this like line over top of the A, and our event A, its complement is going to consist of all the outcomes in which event A does not occur. So going back to our example, our skydiving example, the complement of death from skydiving. So we might want to find the probability of not dying. We can take a more positive spin, right? Of surviving your skydiving jump. So if we do that, we know that there were 3 million jumps total, 21 of them resulted in death. That means that 2,999,979 jumps were survived. So we can find the probability of not dying by taking that 2,999,979 and dividing it by 3 million. And when we do that, we get a probability of 0.999993. Right? So the probability of not dying when making a skydiving jump is 0.9999993. Right? That's a lot of nines. It's more than 3 significant digits. The reason for that is if we rounded to any lower number of significant digits, we would have 1 as our probability, and we don't want to give a probability of 1 unless it really is 100% guaranteed it's going to happen. All right, so this is kind of an exception to that significant digit rule, where if it's not actually 1, we want to show that it's not 1 by continuing out until we would not be rounding up to 1, as they did in this example. All right, so identifying significant results with probability. So rare event rule for inferential statistics. If, under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. That's a lot of words. And let's talk what this means about being significantly less than or significantly greater than, and how we might use probabilities to find this. All right. So using probabilities to determine when they're significantly high or low. So significantly high number of successes means we'll have X successes among N trials, and it's significantly higher number of successes if the probability of X or more successes is unlikely with a probability of 0.05 or less. There's that 0.05 number again. All right, so if the probability of this happening just by chance is 0.05 or less, then we say, you know what, that was a significantly high number of successes, so that assumption probably not right. So similarly, if we do the low thing, same deal. We're looking for a probability of 0.05 or less of X being that small. So an example of this, if we're testing out a drug, like in a drug trial, that's supposed to increase the likelihood that you'll have a boy instead of a girl when you have a baby, then we might assume that about half of the children born would be boys and about half girls. That would be the assumption that we're making. And then we would look at the probability, we'd look at the outcomes of births with people who are using this drug, and we might see that 75 out of 100 births result in a baby boy. And if we see that, then we can calculate the probability that we get 75 out of 100 babies being born as boys. I'll tell you right now, it's very unlikely that that would happen. All right, we get a probability of 0.05 or less that would actually happen. And so we assume, like our assumption that we made, that about the probability of getting a boy was about 0.5, that about 50% would be boys. With that assumption's not true. All right, we have kind of proof that it's not true. We'll be working more with that type of thing as we move forward, but just that general idea, it's there. All right, so our probability review real quick. Probability of an event is a fraction or decimal number. It's got to be between 0 and 1. If it's outside of that, something went wrong somewhere. Probability of an impossible event is 0, and the probability of one that's certain to occur is 1. For notation, we use the capital P of A, all right, for the probability of event A, and the notation probability of A with that line over it for the probability of that the event A does not occur. So now let's talk odds. So there's 3 types of odds. The first one is actual odds against. So the actual odds against event A occurring are the ratio of the probability of A not happening over the probability of A happening. So we usually give this with a colon in between it. So it looks like A to B, all right, where A and B are integers, and what we do is we reduce things. So if we had like A is 16 and B is 4, then we would reduce it down to 4 to 1. Right? You've probably seen ads like this somewhere at some point. The lottery gives them, most gambling situations, especially at racetracks, give odds. If you've ever watched any of the big horse races, they give odds like this. All right? So odds against, probability that it doesn't happen to the probability that it does. Odds in favor is just the same thing flipped over. All right, so now we're going to look at the probability that it does occur to the probability that it does not. All right. And finally, payoff odds. So the payoff odds against event A occurring are the ratio of net profit if you win to the amount bet. So payoff odds against A are going to be our net profit to the amount bet. So let's take a look at an example. So actual odds versus payoff odds. This is important if you ever plan to gamble in your life. All right. So if you bet $5 On number 13 in roulette, your probability of winning is 1 out of 38. Not great odds. But the payoff odds that the casino gives are 35 to 1. Right? So the actual odds against the outcome of 13. Well, if the probability of winning is 1 out of 38, that means the probability of losing is 37 out of 38. So the probability that it's not 13 is 37 out of 38. And the probability that it is 1 out of 38. So we'll take that probability that it's not 13, 37 out of 38, and divide it by the probability that it is 13, 1 out of 38. And when we do that, the denominators, 38s, cancel. And what we are left with is 37 to 1. All right? And we would read that as 37 to 1. So our actual odds against are 37 to 1. So part B is asking, how much net profit would you make if you win by betting $5 on the number 13? So we're going to bet $5 on 13, and we're going to win. So if we do that, because the casino has payoff odds against 13 at 35 to 1, those payoff odds, we read that as our net profit to the amount bet. So $35 is our net profit if we bet $1. Since we bet $5, our net profit will be 5 times $35, or $175. We'll get that net profit back, so we'll get $135 or $175 as our winnings, and we'll get our $5 original bet back. So the total amount that we'll collect is $180 with our net profit of $175. Finally, if the casino was not operating for profit and the payoff odds were changed to match the actual odds against, how much would you win if the outcome were 13? So if the casino were not operating for profit, the payoff odds would, instead of 35 to 1, be 37 to 1. They would be the actual odds against. So the actual odds against were 37 to 1, and if the payoff odds were actually that, then we would get $37 for every $1 we bet, or 37 times $5 for the $5 that we bet, giving us a net profit of $185. So notice the casino is making a profit here by providing a profit to us of only $175 instead of the $185 that would have been paid if the roulette game was completely fair instead of favoring the casino. So casinos make their money because the odds are developed, the payoff odds are developed so that everything is favoring the casino. It's not necessarily that you're not going to win, it's just that when you do, they're paying out less than the actual odds against are.